Good morning, students. Welcome to Complex Analysis live lectures. So, first of all, happy Makar Sankranti. In this lecture, we'll discuss about antiderivatives, a continuous function, and some equivalent characterization of antiderivatives. Okay. We also uh, prove Cauchy theorem. Okay. Let's start with. So, we already seen what is meant by antiderivative. We can again recall quickly. So, antiderivative of a continuous function f of z on a domain D is the function capital F of z, okay, such that f dash of z is equal to f of z, okay, for all z belongs to D. So f dash exists and it is equal to f of z for all z belongs to D. So now we'll see what happens to integration of functions which are having antiderivative. Okay, so we'll give uh, the lemma. So let f of z be a continuous function defined in a domain D. Okay, then the following are equal. We write E F A E. That means the following are equivalent. That f of z has an antiderivative capital F of z. Okay. That means f dash of z is equal to f of z for all z belongs to D. This is same as saying that whenever f of z has an antiderivative, then the integration of f of z or any contour which lies entirely in this D starting from z1 to z. Okay, this is same. That is equal and it is independent of which path, means integration of this f of z, okay, dz over c is starting from z1, okay, and ending with z2. This is same and this value is equal to this f of z2 minus f of z1 where capital F is antiderivative, okay, where for all contours c, okay, uh, starting from z1 and ending with z2, in such a way that the C entirely lies in D. Otherwise, those points F may not be defined. Okay? Such that C entirely lies in D. Okay? So no matter whatever curve we take, this contour, the integration is same. Okay? It means integration is independent of the path we select. Okay? That means if we suppose this is a Z1, this is Z2, either you select this or you select this, okay, or you select something like this, okay, all our integrations are all equal. This, in the other words, we can also say, suppose that is same as saying that integration of f of z dz over c1 same as integration of f of z dz over c. So if you call it, this is c1, this is c2, and that value is equal to f of z2 minus f of z. Okay, that value is equal to f of z2 minus f of. Now, this antiderivative also has another property which says that integration of f of z dz c is equal to 0 for all closed contour, okay, c lying in this c lying entirely in T. So you take any closed contour which completely lies in T, then integration of f of z dz over c is equal to. Okay, so these three statements are equal. So whenever f has antiderivative, then the integration of f does not depend on which path we select. Okay, starting from one point to the other, any path we can select, and integration of f over any closed contour is fine. Let's do this. So we want to prove that one implies two. That means whenever f has an antiderivative, okay, so let capital F of z be an antiderivative of f of z, okay, in D. That means what we know is f dash of z is same as f of z for all z belongs to, right? And we want to show that if you take any contours starting from C1, Z1 to Z2, okay, which is completely lies in D, then integration of this value is equal to. Okay, so let's see here. Uh, if you want, we can start with a contour, or first we can take with a smooth curve. Let's uh, smooth. Let's see a smooth arc, okay, from Z1 to Z2, which lies entirely in D. Okay, so first we take smooth curve. Okay, then we can extend this to any contour also, because the contour is a finitely combination of smooth arc. Okay, fine. For this, we will show that integration of f of z over c is f of z2 minus f of z. Okay, so this c you can write this c as z of t. Okay, which is um, where t is between a and b, right? Then what can you say about integration of f of z dz? With respect to this is integration of f of z of t into z dash of t. Okay, but we can observe that this f of z same as f dash of z. Therefore, this is nothing but integration of a to b capital F dash of z. Of course, it is z of z is a function in t, and z dash of t. But this is nothing but this is same as integration of a to b d by dt of f of z of, okay, t. But by calculus, what we know is this is same as f of z of b, okay, minus f of z of, but this is starting from a and b. That means the f of zb is z2. This is f of z2 minus f of z, right? So therefore, integration of c, which is starting from z1 to z2, is nothing but f of z2 minus f of z. Okay, so if we want to write here from z1 to, okay, that means our z of a is z of a is z1, z of b is, okay, fine. So you can see that here which path you select, it is not a problem. Now this is a smooth arc. Now if we already seen, if you take, and now let's see BA. Now if C is any contour with finitely many finitely many smooth arc joined end to end. Okay, smooth arc CK is joined end to end. So where CK is from the ZK to ZK plus. Then we already know that integration of C over this f of z dz is nothing but summation integration of f of z dz over this each ck. So you can call it k is from 1 to n, finite many. But for each ck, because it is a smooth arc curve, we know already this is the value of, is nothing but capital F of zk plus 1 minus f of zk. And when you expand this summation, only two terms will remain. That is the last one is f of zn plus 1 minus f of z. Okay. So no matter whether you take a smooth arc curve or contour, this integration is does not depend on the path to C. Okay. Now we'll prove 2 implies 3. Okay. So what is meant by 2 implies 3? Assume that the integration of f of z, okay, the integration of f for C1 as C2 is same when you have C1 and C2 are have same starting and end. Then we want to show that integration of Cf of z dz is equal to 0. Okay. To show that 2 to 3, let C be any closed contour, okay, lying in D, completely lying. Now the idea is we'll take 2 points z1 and z2 on C, and from that we will take two different contours. Okay. You can call it C1 and C2. C1 is also starting from Z1 to Z2, and C2 is also from Z1 to Z2. Okay. Then by using second one, integration of those f for C1 and C2 are same, right? So let Z1 and Z2 be 2 points, okay, on C. So let me draw the picture. Suppose assume that this is our closed contour C, okay, completely lying in uh, our domain. Suppose assume that this is our domain, okay, this is our domain D, and this is our C. Okay. Now take 2 points Z1 and Z2. Suppose this is my Z1 and says this is my Z2. Then we'll take two paths C1 and C2. So suppose this is, say this is C1 and this is C. Then what is our C? C is nothing but, you can say up travel here C2, then travel minus C. So C1 minus C2 is, okay. So let C1 and C2 be two contour, okay, with endpoint Z1 and Z2, okay, as shown in the picture, right? Then we can see that this C is nothing but C1 minus, okay, fine. If you want, you take in the anti-clockwise direction also, it is not a problem. If you take like this, then also you can get the answer, right? Then by assumption, because C1 and C2 are two contours, okay, so and whose starting point and end points are same, right? Uh, by assumption, what here is integration of f of z dz over C1 same as integration of f of z over C, right? But then if you simplify this, then what we get is integration of f of z dz, okay, minus, or if you want, you write here plus, this is over C1, this is minus C2, f of z dz. This is equal to 0, but this is same as integration of f of z, okay, dz, C1 minus C2, which is C, is equal to, we prove that integration of f of z over any closed contour is, okay, fine. Now let's prove the other last implication is 3 implies. Okay. That means whenever we have a closed contour C such that f of z dz is 0, then we want to show that f has actually have uh, an antiderivative. That means here what we want to show, we have to somehow define a function capital F and show that it is antiderivative. That means differentiation exists. Okay. First of all, when we define, we show that it is well defined. Then differentiation exists and f dash is same as. Okay. So for that, we'll define. So define capital F of z for z is any point of the domain D as integration of z naught to z f of the s d. Okay. So if you want, you can write fix the point z naught in. So take any point, fix point z naught in D. Then for given any z in D, you define f of z as integration of f of s over the contour starting from z naught to that, okay, f of s. Now because we have shown this, so we will first show that this is well defined. This f is well defined. What is meaning of saying that? That is, whenever z1 is equal to z2, then the value of f of z1 same as f of z2, right? How we can show this? Again, the third one says that if you have any closed contour, okay, C, then integration of f of z over that C is, okay. So here we can have, so let C1 and C2, okay, are two curves starting from Z1 to Z2, okay. Another one is from Z2 to Z2, okay, right? So this meaning of that, so you take this C1 is from Z1, okay, and then this is Z2. The another one you take, okay, Z2, Z2 to Z2. Okay, this if you want, you can take it here is Z2 to Z2. Then C1 plus C2, that will be our C, which is equal to 0. Okay, or if you want, if you take from here to here, then also it is same. Remember, here Z1 and Z2 are same, so we cannot write like this. How will write? We cannot, as Z1 and Z2 are same, right? How we can take here is take this Z0 is already there. Then Z1 we know which is same as Z2. So you take one, suppose this, which is C1, contour from Z0 to Z1. The another one you take is Z0 to Z2, which is same as Z. This is our C. This is our C. So let C1 be a contour from Z0 to Z1, and C2 a contour from Z0 to Z2, but we know which is same as Z, right? So therefore, if we take, then consider C as C1 minus C. So C1 is Z0 to Z1, then minus C2 is from Z1 to Z0. So therefore, you will get a contour from Z0 to, say, closed contour, right? So therefore, by assumption, what we have is integration of C f of z dz, right? But that shows that integration of C, that means integration of f of z dz over C1 is same as integration of f of z dz over C. Okay. But now what is integration of over C1 means it is starting from Z0 and Z1. Okay, that is same as integration of Z0 to Z1 f of z dz. If you want, you can write here ds. Okay. We are using, if you have any confusion, then we can use this as s. Okay, this we can write as s ds. Okay, s ds, because we have defined this in terms of capital F of z, so that is given. Otherwise, we can, okay, this is s, right? This is s ds is equal to integration from z0 to z2 f of s d. But by definition here, you can see that z0 to z, that is f of. So here z0 to z1, that means this is same as f of z1, and this is f of z. Therefore, f is well defined. Now, what we want to show is that our next claim is, we want to show that this next claim show that f dash of z exists and it is same as f of z, small f, small f of z, for all z belong to. So we'll try to find the f of z plus delta z, that limit, and with difference of f of z, and we'll show that it's 0. Okay. Fine. So what we want to find f of z plus delta z minus f of z. Okay. We'll see what is this one, right? So we have to make sure that this z plus delta z, we have to select delta z in such a way that z plus delta z also lies uh, in that domain D. Okay. So choose delta z, okay, such a way that z plus delta z, okay, is in, of course, some neighborhood, is in some neighborhood of z, okay, and this z plus delta z and lies in D. Okay, inside D, this will be. Okay, so let me draw a picture. Suppose this is our D. When I'm saying D, you have to so assume that this is our domain D. Okay, then we have somewhere, suppose this is our Z naught, and say suppose we have Z, then select Z plus delta Z. Okay, so in such a way that Z plus delta Z is also like, then we can have any point thing but S. So here also point is S as integration or that contour we are doing, right? So therefore, with respect to this, what you will get here, we want to know what is this. For that, therefore, f of z plus delta z is nothing but f of z plus delta z is um, is from z naught to z plus delta z f of s d, right? Yeah, and f of course z is from z naught to z f of s ds. Therefore, f of z plus delta z minus f of z is nothing but from z naught to z plus z naught to z plus delta z into f of s ds minus z naught to z f of s ds. Right? You can split this z naught to z and z naught to z plus delta z as z naught to z and z to z plus delta z. Okay, so z naught to z naught to z will get cancelled. So what is remaining here is z to z plus delta z f of s. Okay, so therefore, what we have f of z plus delta z minus f of z upon delta z. Okay, this is nothing but 1 by delta z times the integration of z plus delta z f of s. Now we want to show that this differentiation, this with different by subtracting f of z and taking limit as delta z tends to 0, we want to show that that value is less than equal. Okay. Also, we can observe that this 1 by delta z into here z to z plus delta z f of z d. This one is f of z. That means it is actually outside. You can bring it this outside integration, and z plus delta z times 1 times ds is s, and when you substitute limits, it is delta z. So delta z will get cancelled. So what we have here is, okay. So therefore, f of z plus delta z minus f of z upon delta z minus f of z. If you take these two difference, what we have here is 1 by delta z integration of, okay, this z plus delta z same f of s minus f of z. Okay, so z plus, this is z to z plus delta z. Okay, what we have here is f of s minus f of z d. Okay, this you can see that integrand one is f of s and the other one is f of z. Okay, now because f is given to be continuous, so whenever we have, since f is continuous for given epsilon greater than 0, there exists a delta greater than 0 such that whenever mod s minus z is less than delta, then what we have is mod f of s minus f of z is less than x. Okay. Now we start with an epsilon. Okay. Then there is a delta here, right? Such that mod s minus z is less than delta, like, right? So if you see here, we have when we have selected chosen this delta z, we have to make sure that z plus delta z is in neighborhood of z. Okay. So that neighborhood what we will take here is less than 10. Okay. That means so choose this delta z such that this modulus of delta z is less than 10. Okay. Then for this epsilon, what we can observe here is that so you go to this picture again here. So this is point S. Anyone, if you want, you can make it as a straight line or no problem. So if this is the point anywhere this S and length from Z to Z plus delta Z. Okay, so then S minus Z. The difference between this S minus Z is always less than the difference between Z plus delta Z and Z. Right? We can take that. Then this mod S minus Z, okay, is less than or equal to Z plus delta Z Z, which is nothing but delta Z, and it is less than Z, right? So if you take any S, okay, so for all S on the curve, on the contour Z to Z plus delta. Okay. So therefore, for all those points S, this implies mod f of S minus f of Z is less than, right? Therefore, if you take this modulus, therefore modulus of f of z plus delta z minus f of z upon delta z, right, minus small f of z is less than, okay, this is equal to 1 by mod delta z, right, and modulus, if you take integration inside modulus, then this is less than or equal to 1 by mod delta z, okay, in integration of this z to z plus delta z minus f of z minus f of s minus f of, or f of z minus f of, whatever you say, okay, into d, right? Now we can see that we can use this is less than epsilon. It is true for all s here. So epsilon will come outside. This epsilon into epsilon by delta z. Okay. Then this is z plus delta z, right? Minus z plus delta z minus delta z, right? Therefore, what we will have here is equal to, right? Therefore, modulus as delta z tends to 0, then what we have here is less than epsilon. That means, therefore, limit of f of z plus delta z minus f of z upon delta z as delta z tends to 0, right? This is equal to this value, this f of z. Where epsilon is arbitrary, so by taking epsilon as small as possible, we can make it this is equal to the limit as delta z tends to 0. This is right. That shows that this implies f dash of z, okay, is equal to f of z. This is true for all z belongs to. That shows that implies f of z as an antiderivative capital F. Okay, that completes the proof of this theorem. Remember, this theorem says that if any one of among three one exists, then remaining two is. That means if we know that f has antiderivative, then we can apply any one of these. Or if we know that the second condition is true for all such contours, then we can say that f has antiderivative or third. Okay. Let's quickly see one or two examples how we can have apply this integral antiderivative to calculate integral. Okay. So, example, uh, book itself. Suppose if we quickly take f of z is equal to 1 by z square, then we know that it is continuous, okay, everywhere except at z is equal to. So if you take the entire plane minus 0, that is your domain, then on this it is continuous, right? So, um, so you take your d as say suppose mod z greater than, right? Then integration of C, you can take where C is any positively oriented circle. So let C be a positively oriented circle. Z is equal to 2 into e power I theta, where theta is from -pi to pi. Okay, fine. Then we can see that integration of f of z over c dz is nothing but, because for f of z we have antiderivative is namely -1 by z. Okay, if we take -1 by z, then this uh, has antiderivative, right? So therefore integration of f of z dz is simply nothing but the starting point and end point are same. So you can use the third point of that, and you can say that this value is equal to 0. Since what is the reason? Since this f of z has antiderivative, antiderivative, namely capital F of z is equal to -1 by z, and this domain D, which is mod z greater than. Okay, fine. Now we'll see one example which involves branches, then how we can calculate the integration over a contour which involves branch or branch. Okay. So let f of z, which is equal to say 1 by z. Okay. Then even though it has antiderivative, we know antiderivative is log z, but log has is a multi-valued function and it has branch. Okay. So if we take a contour, say suppose then take this c. C is same. Z is equal to into e power I theta minus theta is equal to pi. Then how this look like? Picture is um, so you can take a C. This is from, okay, minus this. If you take this is 2i and this is minus 2i, and this is your C. Okay. Then what we can observe here is that in last class also we have discussed earlier this line, okay, any line passing from this origin, this is a branch. Okay. So because of this branch cut you have here, so at this point your log is not defined at this point. Okay, so there is a problem, you cannot directly apply the previous reason, because for that we require that f dash of z should be defined at all point. Here this point is at this point, capital F of z is antiderivative does not define. Here in this example it is log, right? So how we'll do this? We'll try to do it using, we'll split this or we'll divide this c into two parts. Okay. So let me draw that. So we'll consider the same one. This is the c1, okay, which is from minus 2i to 2i. The other one, uh, at that time, uh, at that time we will consider this as a, this is our brand which doesn't cut. The other one also we can take the other part. Okay. So the other part, I will take it as here. This is our C. Okay. Then C is nothing but C1 C2. Okay. Then we will find the integration over C1, integration over C2, and we will add. Okay. And you can see that when we have considered this C1, we will consider a particular type of branch. Okay. Namely principal branch we can take. And when we are taking here, we will take another branch, and which is analytic. Okay. Because that doesn't contain these points. So it makes it, right? Fine. So here C1, what is this? C1 is from, huh? So here theta you can take from minus pi by 2 to pi by 2. Okay. And here your theta is from pi by 2 to pi by 2. This is your C, right? So in this case, what should be our f of z? The single valued function capital F of z. capital F of Z for C1, we'll consider for C1, so which is this is nothing but log. Okay, that is the antiderivative of this Z, right? Where mod Z greater than 0. Okay, or if you want this, you write natural logarithm of R plus I times this theta, where R is greater than 0 and theta is from the principal minus pi to pi. Okay. Between, then therefore integration of, now you can observe that this whatever points we are considering, it is defined everywhere, there is no problem. Therefore integration of this f of c1 dz is nothing but what is this? This is nothing but the value of this antiderivative and evaluated at the points from minus 2i to 2i. Okay, so this is f of 2i minus f of minus. Okay, so this is endpoint and this is start. This is same as capital log of I minus capital log of minus 2i. Okay, this is same as natural logarithm of 2 plus I times pi by 2. You can check that, it is not a problem. Similarly, this one is this minus I pi by 2. Okay, fine. I ask you to verify. Simply find out capital log. Right? Therefore, this is same as I pi by 2 plus I pi by 2, which is right. Similarly, for C2, for the curve C2, what we'll take? We'll take this f of z for this one of the branch as natural logarithm of r plus I times theta, where r is greater than 0 and theta is between pi by 0 to 2 pi. Okay, this is of course our log, right? Remember what is our C2? C2 is 2 times r, that means e power I, where theta is from pi by 2 to 3 pi, right? Fine. Therefore, integration of f of z over C2 dz is nothing but this log z2, which is starting from this pi by 2, right, to 3 pi by 2, right? So this is nothing but log z from 2i minus 2. Okay, you can see here from C2, this is 2i and this is minus 2i. So 2i to minus 2, therefore f of b minus f of b, like, right? This is nothing but log minus 2i minus log, this is small log, right? And you can check that this value is natural logarithm of 2 times by 2 minus of this natural logarithm of 2 plus I times. Okay. Then again this 2 will get cancelled. What we have here is again I pi. Therefore, integration of f of z dz over c is integration of f of z over c1, okay, plus integration of f of z over c2. This I pi plus I pi. This is nothing but 2i 2 pi. Okay. So this is how we can find integration where this f of z has branch. Okay. So we have to select C1 and C2 in such a way that they eliminate the branch. Okay. Then you take the sum. Now we'll come to one more result, which is interesting. So if you see, so far what we have seen is that if f of z has an antiderivative, then integration of f of z over c, where c is any closed contour lying in that domain D, then integration of that value is integration of f of z over c is 0. Okay. So similarly, we can have a result which says that by due to by Cauchy, uh, this is says that if f has f is continuous and this f dash is continuous, f is analytic and f dash is continuous, then integration of f of z over c, where c is any closed contour So let me write here. This is Cauchy theorem, and we'll prove that. Okay. So what is the statement? Is let R be a closed region consisting of all point interior and on the closed contour C. Okay. Then uh, if is R and f dash is continuous, f dash is continuous, okay, in R, then integration of f over C is 0. Okay. So of course, one may see that what is this one. Later, we will see that that is due to Cauchy theorem, which says that if f is analytic in a R where R is closed region containing this interior and points of C, then integration of f of z dz is equal to 0. Okay. That means this f dash is continuous is not required. That one can drop. Okay. Or later, when we prove further results, if f is analytic, then it has all derivative of all order. Okay, then obviously this is true, right? But he is the one who initially proved this when we don't have the result that if f is analytic, then all derivatives of f. Okay, fine. Otherwise, if you know that f is analytic, then derivatives of all orders of f exist, then this is obvious. You don't need to assume this. Okay, but when Cauchy did that at that time, it was not. So proof is not calculation and the use of result called Green's. Okay, we'll come to that Green's theorem, and when first we want to show that this integration of f of z is we know by f of z of t, if you write as parameterization into z dash of t dt, where our c is z of, okay, where t is from a to. Now what we do is we'll try to put this f of z, which is u x comma y, and x is a function of t because this is z of t, which is x of t plus I times y of t. Okay. So if we substitute all those things, so z of f of z of t is u of x of t comma y of t plus I times t of x of t comma y of t. Okay. And what is our z dash of t is x dash of t plus I times y dash of t. And if we substitute these things, therefore integration of t f of z dz will become integration from a to b. This is u x of t comma y of t plus I times p x of t comma y of t, okay, into z dash of t, which is x dash of t plus I times y dash of t dt. Now if we multiply basic as a basic product, this is u, okay, x of t, u of x of t comma y of t into x dash of t dt, right? Similarly, this dt we can put it at the end. Similarly, this I into I square, so this will become v of x of t comma y of t, okay, v of x of t comma y of t into y dash of t, and what we have here dt, then plus I times integration of a to b uh, u of x of t comma y of t into y dash of t plus this I into this. That means what you will have here is p of of t comma y of t into x dash of t. Okay. Now we can write this x dash of t into dt because x of t, x is the function of t, so therefore x dash of t into dt is nothing but d by dx of x. So you can simply write this as dx. Therefore this you can write as a to b u, this is u, okay, x comma y. This x dash of t into dt you can write as simply dx. Okay, this is u minus v into dx. Okay, or if you want to write, this is 2x y of t, x dash of t into dt is dx. Okay, this take little time. U dx. Similarly, v y dash of t dt is nothing but dy. So this will become v dy. I to b. Similarly, u y dash of t dt is y dy. So u dy plus v. Okay. Now what we use here is called this Green's theorem. We use this result. Okay. Result which will be used here is nothing but if we have p real function in two variables and q, okay, which are continuous, whose first order partial derivatives, so first order derivatives are continuous. Okay, are continuous in this region R, given region R, then integration of this p dx plus q dy over given curve C is nothing but the double integration over the region R. This is qx minus py. Okay, this is double it. So you can write dr ds, but basically I'm not writing completely. This is the basic and one that if you have two functions whose first order partial derivatives exist and are continuous, then this is the value. Okay. Now we will apply Green's theorem two times. One is one time here, the another time is this, right? So this u and v, right? Because our since our f dash since by the time it takes identify this pen, since our f dash is continuous, dash, because f is u plus iv, so f dash is ux, okay, ux plus I, which is also same as by using CR equations. So this is continuous. Ux is equal to Vy minus Dx is equal to minus Uy. Okay. So what we know is that since f dash is continuous, that means this U, Ux, Uy, Vx, and Vy, they are all continuous, right? So therefore, if you take this as P and this as Q, then they are continuous. So we can apply the Green's theorem. Therefore, integration of C, what is our u dx minus u dx minus v dy. This is nothing but, so this is our P and this is our Q. So this here is Q is minus. So here what you will get is minus Px and minus Uy. Okay, this you will. You are given the region R. And similarly, integration of the other one is here u dy plus v dx. So u dy plus v dx. So you can write that as v dx plus u dy. So v dx plus u dy. So this is your p and this is your q. So this is nothing but q x. So this is ux, okay, minus this is p, and we want to differentiate with respect to y, so this will become v, okay, over that v, right? But what we know is that, so therefore, if you want, you can replace this by these values. Therefore, integration of f of z dz over that c is nothing but double integration of, first one is minus vx minus uy dA plus I times this ux minus vy to d. But as CR equations are satisfied, uh, since CR equations hold, what we have here is ux is equal to vy and vx is equal to minus uy. So ux is equal to vy, right? So ux is equal to vy, so therefore this is 0, and vx is equal to minus uy. That means this minus uy will become plus vx, so you will get this r, that implies minus vx minus uy 0, and ux minus vy is equal to 0. So therefore this integrand is 0, this integrand is 0. That means that integration of f of z dz over c is equal to, okay, fine. So this is initial result about for which functions f the integrand value is 0. In next class, what we will see is one of the central results called Cauchy theorem. Okay, so this is, which says that if f is analytic, we can drop the condition that f dash is continuous. Okay? If f is analytic, then we can integration of f dz over any given closed contour C is 0. Okay? That we'll prove it next class, which is one of the important result in complex.